So yeah, welcome everybody. We're going to talk about time and give you an introduction to timely data flow. And as Timo mentioned, my name is Malte, this is Nicolas. We are working in a software consultancy which we co-founded called Clockworks. And we're also using the timely data flow ecosystem there to drive our business and help companies with their data journeys. And the timely ecosystem was originally invented by Frank McSherry. And we also did research at ETH Zurich, and I'm still researching at ETH Zurich Systems Group into timely data flow under the supervision of Vasia Calavri. So, if we look at stream processing generally, what we think would be cool to reach is a trifecta of timeliness, consistency, and expressivity. So what do we mean by that? By timeliness, we mean, on the one hand, we want to do very low latency computations, and on the other hand, this also means the time that it takes some new data that flows into our system until an end user actually sees updated results. Secondly, we also want to make sure these results are actually correct. So of course, we're interested in consistency, and in a streaming system, we often face issues such as late arrivals, and so we have to handle this in some way. Lastly, we are interested in expressive computations. For example, if you take a traditional relational database, you have even support for recursive queries and very complex computations, and we would like to translate this into a streaming setting as well. If we are just focusing on timeliness, we could just use naive stateless processing. So we just stream in some data, compute something on it, and stream it out right as we computed something. Of course, this gives us great latency characteristics, but we face the issue of late arrivals, and we also can't support very complex computations since we're stateless. If we focus on consistency, a nice use case would be batch processing. So for example, the MapReduce model. By definition, we don't have any late results because we'll just, if we see some new results, we'll just restart our computation from scratch. And it's also quite easy to scale, especially the mapping stage in a MapReduce cluster. But again, we also have an issue with complex computations since we have to fit this MapReduce model with all the computations we are doing. And since we're in the batch processing world, of course, we have higher latencies. Lastly, if we focus on consistency and expressivity, we could just say, well, let's use a database, since we have the asset properties giving us consistency guarantees, and we are very expressive. So this is like the pinnacle of interaction with the system. We have even support for declarative and recursive queries. But since we're talking about stream processing, this can't be a solution, since we're now using a database and not stream processing anymore. So, how do we obtain this trifecta? And maybe also, why do we even care? And to motivate that a little bit more, we're introducing a small use case we're going to come back to time and again during this presentation, which should give you Kafka superpowers. And it's not entirely true that this is new. It gives you kind of database superpowers, since in a database, the way you interact with the database, writing queries, is completely decoupled from the way data is physically represented in the system. So, for example, in a relational database, you're using tables and rows and columns and tuples, but this is disconnected and decoupled from the way you interact with the database. However, if you use Kafka, we complex physical representation and your downstream use case. You first have to decide in what format your data is in your Kafka cluster, using events, using partitions, and if you then have some downstream system that needs this data in a very special format, you're facing trade-offs, right? You say, well, okay, we have some complex logic in our consumers that join these data together again, or you have to just duplicate logic on the event streaming side so that you can feed it in the correct format to your downstream consumers. But if you're doing that, you're just introducing redundancy, so that is inefficient and increases your maintenance load. So what we propose is that we, again, decouple streaming and decouple the physical representation from the business logic. And we do this by virtualizing partitions. So first, we would to virtualize, we have to somehow repartition our partitions, maybe even across topics. And this also means we have to think about joins now, since these virtual partitions need to aggregate data and relate data to each other from various partitions. Secondly, the virtual partitions themselves have to have some notion about time. Since now you have data from two partitions flowing in, they are both time-stamped, and somehow you have to relate that these events with each other in a way that makes sense. Lastly, to walk the last mile to your actual business logic and downstream applications, you kind of have to get this data out there, and a very modern way to do this, we think, is using reactivity. So, for example, registering a query on the client side, and then your data and the updates, as soon as new data arrives into the system, is just fed to the user without him needing to ask for it.
Can you get this? Cool. Do you hear me? Okay, nice. So, one way to think about a problem like that is the so-called Dataflow model. In the Dataflow model, what you do is, upfront, you describe the structure of your computation using a graph just like that, where nodes in the graph correspond to any kind of operators that perform a function in your computation, so mapping, filtering, joining, all of that stuff, and where the edges indicate the pathways along which data can flow between these operators. So to map this to this Kafka example, we'd have the source operators reading in parallel, ideally, from all of these different Kafka partitions. Then we have a bunch of computational operators merging it together. And finally, we have output operators called sinks that connect to our clients and maintain these virtualized representations that Malte just talked about. The benefit of kind of settling on a structure for your computation up front is incredibly easy distribution. Because if you look at this, we can make copies of the data flow structure and simply shard all of our input data between identical copies of our operators. And so we're kind of doing what Kafka is doing when it's partitioning data physically, and here we can partition data onto our different operators. And if we then take these operator copies and put them onto different physical workers, so threads or machines in our cluster, we achieve true distribution of our computation. Okay, now if we look at an incredibly simple data flow with just a single operator, I've called this operator sum, and the idea is that it receives time-stamped inputs, so each input count carries a logical time indicating at which logical time this input is supposed to have happened, and the operator is supposed to report the cumulative sum of all of these inputs. And crucially, it's supposed to report the cumulative sum as of a consistent logical time, so incorporating all of the data from a logical timestamp, just like a database would. So if you play this through and we ingest the first tuple, this first tuple carries the count of 1 and is marked for the timestamp T0. We simply report the sum of 1. For the next tuple, it is marked for the timestamp T1, and so we report the updated sum of 5. And now we are hit with a late arrival because we ingest a tuple that is marked for the timestamp T0, for which we already reported in a result. So now we violated the basic consistency guarantee because what we reported for T0 contradicts itself, and we did not reflect the entire state of our database at timestamp T0. So this is the fundamental consistency issue that we're talking about, and at its heart, timely data flow is an engine for describing and executing these distributed data flow computations that prevent precisely this kind of consistency issue through a mechanism called progress tracking.
So if we now revisit our example with progress tracking, the first thing you might notice is that we have now, in addition to the data plane, introduced a progress or control plane. And you can think about these progress messages as similar to watermarks and other streaming systems such as Flink. And also our operator now keeps track of at what times it can still expect to see data. So currently we're at the start of our system, so our operator can still see data for every time starting with T0. And if we now process the first record at 1 and T0, this also communicates to the operator there still might be more to come at T0. So we can't output a correct result yet, but have to store it within our operator. Similarly, if we now ingest 4 at T1, we still provide this message, well, there might be more to come at T0, so we still can't output a correct result. But now, when we ingest 3 at T0, we communicate to our operator data will only be arriving starting from T2 onwards. So now for T0, we can create the correct cumulative sum of 4, and for T1, we can also do that to arrive at 8. And this way, we have solved the central consistency issue we faced before. Returning to our Kafka example, this very basic operator is cool, but we need more complex operators, for example, join operators. So in this case, we're using a clickstream topic and a metadata topic holding some kind of configuration that we want to join to this clickstream topic for downstream analysis. And an issue that arises here is that we're seeing streams with very different event frequencies. So our metadata topic only has one config right now, and this never changes. So if we now think about what would happen with the way we did it before, we would ingest 1 in T0 and the metadata config, and the progress messages are T1 and T0, and we're probably going to take the minimum, so our join operator still works correctly. But then we are stuck at T0. So our metadata topic is indefinitely blocking our clickstream topic and our overall progress. So how do we solve this? And this is where timely really shines. It introduces a multidimensional time semantic. So this time, we're tracking sources along independent timelines. And this way, when we now ingest something at T1, so from the clickstream topic, and join it with the metadata topic, we can just independently look at our timestamps and produce a correct result as of that combination of times. So since we're advancing our progress to T1 with our clickstream topic, we can output a correct result for T0. And since our metadata topic holds T0, we can use the combination. And we don't violate our consistency guarantee since this combination is unique. We will never see a combination of T1 and T0 in our system as a result again. Lastly, these progress messages can also be used to communicate progress downstream to further operators, and this is also how progress tracking propagates through your whole data flow. So again, we can join, and all works out fine. How does this actually look in Timely? So this is a real Timely data flow implemented in Rust. And the first thing to notice is that we always write Timely data flows from the perspective of a single worker. This is also a cool thing about the data flow model. At the stage where we write our computation, we don't have to care about parallelization or distribution, since we can parallelize later on. So we write from the perspective of a single worker. Then we create our data flow structure itself, which is very simple in this case. It's just an input operator, then we exchange some data across workers, and then we inspect it and probe it. And this is the first stage, so we create the data flow, and after that follows the second stage, actually running the data flow by feeding it data. And this looks very simple, and it is very simple because we have all these small decoupled operators, but as you can see, we can compose this into much larger and more complex data flows, while still, in the end, using these very simple operators such as a map or a concatenate. If we now revisit our example, we can check what we've achieved so far, and we will actually see that we've achieved the virtualization part of things, because we can do repartitioning using the data flow model and exchange operators, and we can use joins correctly as I showed you before. Also, in the actual virtual partitions, since we have rich time semantics, we can enforce time orders that make sense for downstream consumers. And this is what Timely has given us so far.
So what's missing from this is the last mile issue. So how does the data from our virtual partitions actually arrive at our consumers, at our downstream consumers, and how do we create these partitions? Ideally, we would like a higher level abstraction than writing all of these data flows by hand. So we would like an interaction model similar to a database again, where we maybe issue a query and have the data flow be created for us automatically. And so if we kind of put this into this image of the trifecta that we talked about earlier, what we saw now is how Timely allows us to navigate this trade-off between the speed at which we produce results and our correctness. So we achieve timely results without while still providing strong consistency guarantees. And what's missing is the expressivity corner. And we'd argue, like if you think of your favorite algorithm, there's probably a loop somewhere in there. And it's the same for queries. So if we think about the complex kinds of queries that people could ask of our system, they always involve recursion. And you might ask, why is that? And the reason for that is that for complex use cases, usually we deal with data that is relational, so that looks more like a graph and less like a simple list. And if you want to know anything interesting about a graph, most of the time you start with your nodes and your edges, and you start from some interesting node that you know about. So in this case, we have this very small graph with just a few nodes, and we have the starting node C. And from that, we perform an iterative exploration of this graph to compute some properties. So for example, here we go breadth first. We explore all of the edges reachable from C. So in the first iteration of our computation, we discover the nodes A, B, D, E, and we do something with them. And then we perform a second iteration of our graph to reveal the final node F and arrive at the final result for computation. And this is why we mean that there is this mapping between complex queries and graph traversal. And if we think about how we would write a data flow like that in Timely, it would look much like the following. It actually does look like the thing on the left. With all kinds of operators that seem very familiar by now, so maps and filters and joins. The only thing that's different is now we have this thing called iterate. And what the iterate operator does, it creates a data flow like the one on the right, so a data flow that feeds data back into itself, a data flow with a cycle. And if you think about it, for something simple like a breadth-first search, it makes a lot of sense because one input of our breadth-first search is the stream of changes describing our graph. So new edges and edges that are removed and how the graph evolves over time. The output of our breadth-first search is, for example, the set of nodes that are reachable from our starting node. And the feedback edge that loops back into the data flow reports the transitive edges that we discover as we iterate through this graph. Now, this looks a lot like the problem that we had with the join operator with two inputs, because again, we can run into an issue where the feedback edge, for example, is blocking the input edge and vice versa. And why is that? So if we again think about the changes to our graph in terms of database transactions, so we get updates at T0, T1, T2, etc., we have to perform all of the iterations for transaction T0 before we can start processing subsequent transactions. Because, intuitively, if we have multiple transactions in flight, the graph is still evolving underneath your feet, right? And so transaction 1 might see a state of the graph that was never meant to be visible to anyone because transaction 0 is not finished yet. So we're violating the isolation principle that we know from databases. Still, this is annoying again because now we're blocking all of the transactions that we would want to run, especially in a parallel setting. We would know how to interleave the computation. We've already seen that we can introduce another dimension of timestamps to have multiple transactions flow through the graph, no problem, because in this case, the second dimension that we would introduce would be the iteration depth, so the number of times we went around the cycle. And this would allow us to interleave the computation, but now we have to think about how to ensure the consistency guarantees that we violated. And if we think about what we did for the join example earlier, when we didn't really enforce anything interesting because the consistency guarantees were very simple. We always wanted that new data on one input could see the most recent version of any data on the other input because we didn't care about the temporal relations before. And this, if you draw a kind of a visibility table of what each transaction can see while it's being processed, you obtain something like this, which we draw for the transaction that happens at clickstream time T2 and metadata time T2. And this transaction can see all of the previous inputs on either of the transactions, so it can, on either of the inputs. So it can even see transaction 3 on the metadata topic if that is already available. And so we have kind of, we just hand everything through as soon as we see it. With iteration, things get more complex because, as I explained, while one transaction is iteratively exploring the graph, we have to be careful that subsequent transactions cannot yet see this fluctuating state of the graph. So in this case, we have to restrict the visibility of each transaction. And to do that, in this case, we use something called a product partial order that gives us a table that looks like this one. So here, as you can see, again, for the second iteration of transaction 2, we only can see up to the second iteration of any previous transactions, so that we can make sure that we only see committed data from all of the previous transactions. And if we, so there's many different orders that you can think about for different use cases. For iteration, it usually boils down to this. And this way, we can make sure that while we're interleaving all of these transactions, each one can only see a state of the graph that is consistent, that is already committed to by all of the transactions being processed concurrently. And still, there's one issue. You might think that in a streaming setting, we could not possibly do more complex graph computations in that setting like we do in a database if we have to start from scratch with every new input. And that is true, especially for very large graphs. So what we want is our graph computations to be incrementalized. So to only update in response to changes instead of starting from scratch on every new input. And luckily, there is an extension of timely data flow called differential data flow that provides us with a set of functional relational operators, so join and reductions, that allow us to compose iterative incrementalized computations. So computations that look like they are written like a database query, but they actually execute only in response to changes and update very efficiently. And any valid differential data flow is actually also a valid timely data flow because it just uses timely under the hood for execution. And the performance of this approach works in practice and we think also speaks for itself. So here, for example, we are computing the connected component structure of a social network graph, so to find interrelated groups of people, for example. And we have all of these different systems using over 100 cores to find this structure initially. And even on a single core, differential is already outperforming them for, or at least matching their performance for evaluating the initial structure of the graph. Still, differential, as we saw, we can simply scale the computation by distributing our data flow onto multiple workers. So as you can see there, for example, for the life journal graph, differential took 20 seconds to compute the initial result with a single core. And as we go to 2 cores, this roughly cuts in half. So it does scale as we add more threads and machines. And then the most salient row probably is the one on the bottom because that gives the time that it took differential to update the computation once it computed the initial result and change happened to our graph. Differential only took a few hundred microseconds to update the strongly connected component structure in response to that, whereas all the other systems would have to start from scratch. And this is really where kind of the practicality of differential in a streaming setting comes through. Okay, so we've seen how to write all of these recursive graph-style explorative queries. And with this set of operators, we have all the basic tools that we need to implement a high-level relational query language, such as SQL or GraphQL or Datalog in our case. And we actually built this project called 3DF, short for Declarative Differential Dataflows, that implements an interactive Datalog engine over differential data flow that gives you precisely these semantics of queries that update in response to new data. And we'd argue that in doing this and presenting this stack, we have kind of reached the trifecta of stream processing because we described how to model very expressive computations without giving up either the low latency that we want from a modern stream processor or the consistency guarantees that we would want from a database.
Finally, if we now one last time revisit our example, we can see that besides virtualization and virtual partitions, we can also check the reactivity box, since we can now use something like 3DF to issue queries against these streams that we have created and get returned in a reactive manner results as they flow into our system. And you might have guessed it, this is not only something that we thought about in theory, but of course, we actually implemented it. So if you're interested, feel free to check out clockworks.io/kplex, that's what it's called, or of course, come speak to us after the talk. In summary, we have introduced Timely Dataflow to you, a stream processing framework or a stream processing computational model that uses data flows with multidimensional progress tracking to ensure low latency data flows while still remaining consistent. And we've also introduced to you differential data flow, which extends timely data flow with iterative and incrementalized operators, opening up even more opportunities, especially concerning expressivity. And lastly, we leverage differential data flow and showed you 3DF, which is giving you streaming relational queries so that you can really interact with a streaming system as if it was a database. And this is also the reason why we like to think about Timely as not only just some other kind of stream processor, but as a true computational model which you can use to write distributed systems while still staying sane. And with that, we thank you for your attention and are happy to take your questions.
Thanks for the talk. Can you give us a couple of real-world examples of systems that are using Timely? And
sure. So from the publicly visible point of view, probably there's very few right now. But so we've built commercial projects for clients of us. So for example, distributed GraphQL engines with like to match up historic data, query historic data that is kind of unifying both like the batch use case for obtaining data sets and the online use case for kind of updating them. And so this kind of system, basically anything where you have a big ETL pipeline and maybe the data is not in the right formats and you maybe have performance issues with your Spark cluster, that is where you'd use a Timely system to do the same job, but do it faster.